Professor Belfrost's science class is back.
Hi, welcome back to my channel. Today you are with me on physics class, and yeah, we have now stepped onto a new chapter, still related to the previous chapter, which is kinematics, but in this chapter we'll focus on a two-dimensional way to view the kinematics chapter. This is the first video, and I'll make about 4 to 5 videos on this second chapter. Okay, so yeah, let's take a look at it. Example. So suppose you want to walk from one point to another in a city with uniform square blocks as shown in the figure below. You don't need to know the size of the grid. Okay, this is not important here. So the straight line path that helicopter might fly is blocked. So you took another kind of two-dimensional path as shown. So you walk 4 blocks in all, which is 9 east followed by 5 north. So what is the straight line distance? Okay, it says that short distance is always a straight line. So you can do Pythagorean theorem, and by pointing to the Pythagorean theorem before, you know that the direct or straight line path between the 2 points that you want to go is that it is about 10.3 blocks in three significant figures. Okay, and it is considerably shorter than the following blocks that you need to walk. Okay, and yeah, so I've also discussed about the difference between the total distance and displacement on the previous chapters, and I really hope that you understand this concept well. Okay, so the fact that a straight line distance in a figure above is less than a total distance walk is one example of a general characteristic of vectors. So vectors are quantities that have both magnitude and directions. So as for one-dimensional kinematics, we use arrows to represent vectors, and the length of the arrow is proportional to the vector's magnitude. And the arrow's length is indicated by hash mark in figures uh, before. Okay, so you see the hash mark. Okay, so the arrow points in the same direction as the vector, and for two-dimensional motion, and the path of an object can be represented with three vectors. So one vector shows the straight line path between the initial and final point of the motion. Okay, you see it by starting to the destination. One vector shows the horizontal component of the motion. Okay, the 9 block is vector, and one vector shows the vector component of the vertical motion, which is the 5 block north motion. Okay, so these together give straight line path if we add it vectorically. Okay, so yeah, this is just the explanation from the previous figure. So the factor that we are adding are perpendicular to each other and thus form a right triangle, and this means that we can use the Pythagorean theorem to calculate the magnitude of the total displacement. The person taking the path shown in the last figure walks east and then north. Okay, and how far they walk is unaffected by the motion eastward, and also similarly how far they walk north is also affected by only the motion northward. So here's the theorem of independence of motion that states that the horizontal and vertical components of two-dimensional motion are independent of each other, and any motion in the horizontal direction doesn't affect motion in the vertical direction and vice versa. That this is true in a simple scenario like that of walking in one direction first, followed by another. But this is also true of more complicated motion involving movement in two directions at once. Take an example, say that we compare motion of two baseballs. So one baseball is dropped from rest, and at the same instant another is thrown horizontally from the same height and follow a curved path as shown by a stroboscope, which is depicted in the figure. So it's remarkable that each flash of the stroke and the vertical position of the two balls are always the same, and the similarity implies that the vertical motion is independent of where all the ball is moving horizontal. But you need to take into account that this is by assuming that there's no air resistance here, so the vertical motion of a falling object is only influenced by gravity, not by the horizontal force. So this is very important. No air resistance. Okay, so careful examination of the ball thrown horizontally is also show that it travels the same horizontal distance between flashes, and this due fact that there are no additional forces like air resistance, etc. So the horizontal velocity is constant and affected neither by vertical motion nor by gravity. Okay, so two-dimensional curved path of the horizontal thrown ball is composed of two independent one-dimensional motions, which is horizontal and vertical, and the key to analyzing such motion, called a projectile motion, is to resolve or to break it into motions along perpendicular direction. And resolving two-dimensional motion into perpendicular component is possible because the components are independent. So here's we learn how to do addition and subtraction factor by analytical way. Okay, this is we have talked before, so factors, quantity, and direction. Okay, so in one dimension that you can use, the direction can be expressed by simply putting plus or minus sign before the magnitude, right? It's very simple. But for the two dimension, we need to specify the direction of a vector relative to some reference frame and using an arrow having length proportional to the vector's magnitude and pointing in the direction of the vector. So you need to state the theta. Okay, that is the direction. Okay, theta, for example, I write that this is 35-degree south from west. Okay, for example, like this. Okay, so here's the figure show you a graphical representation of a vector using an example that we have discussed before. So the boldface symbol such as D, which stands for a vector, and its magnitude is written or represented by its symbol in italics, which is D italics. Actually, it's not bolded. Okay, it's not intentionally bolded. Okay, or because I usually write it uh I really don't like to edit it. Okay, so I always write it in absolute mark. Okay, it also represent the magnitude. So you have D written in absolute, and it also represent the magnitude. And its direction is simply theta. Okay. So first I discuss about the head to tail, not head to tail. Okay, head to tail. I mistyped it again. Method to do factor addition. So head to tail method is a graphical way to add factors. This is described in a figure. On the right side, actually not below, I've changed the position. On the right side of the slide and the steps following. So the tail of the factor is the starting point of the factor, and the head or tip of a factor is the final point, the end of the arrow. Okay, so you can see it. Okay, so here's the description. So for step A, the you draw a factor representing the displacement to the east, which is 9 units in the case. Then we draw a factor representing the displacement to the north, which is 5 units in this case. And tell this factor to originate from the head of the first east pointing factor. Okay, and C is that we draw a line from tail of the east pointing factor to the head of the north pointing factor to form the sum or resulting or the resultant factor, which is D, denoted by D in this case. So the length of the arrow D is proportional to the factor's magnitude and is measured using a ruler, okay, to be 10.3 units, okay, and its direction described as the angle with respect to the east or horizontal axis. Theta is measured using a protector, and it can be said to be about 29.1 degrees. Okay, so here's the example, the problem that will make you understand this concept clearer. So using the graphical technique for adding factors to find the total displacement of a person, blah 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 blah. So first she walks 25 meters in the direction of 49 north of east, then she walks 23 heading 15 north of east, and finally she turns out walking 32 meters in direction 68 south of east. So how to solve it? First draw. the three displacement factor. Second is place the factor head to tail retaining both the initial magnetic and direction. Third is to draw the resultant factor R. So these three steps is shown in the three figures on the bottom side of the slide. For the fourth one is on the next slide. Okay, so using a ruler to measure the magnitude of R and using protector to measure the direction of R. Okay, like this. Okay, and actually you can do another way. Okay, so you can work like showing the figure on the right side. Okay, so you add it in a different way. Okay, and you still can get the same solution because actually factor doesn't mind if you want to do from which step, and it will gives you the same solution. Okay, here we see that when the same factors are added in different order, that the result is the same. That this characteristic is called the factor addition is with commutative property. Okay, so a plus b is essentially the same as b plus a. Okay, this is like the ordinary addition. Okay, or summation. Now let's discuss about factor subtraction. Actually, factor subtraction is the sibling of the factor addition. This is very simple. So factor subtraction is a straightforward extension of factor addition. I've told you before that to define subtraction, say that we want to subtract the factor b from factor a, which is written as a minus b, that we must first define what is actually minus b. So the negative factor of b is actually defined to be written as minus b. But this is actually graphically the negative of any factor which has the same magnitude but the opposite direction. Okay, it's shown in the figure below. So you see it's pointing on the opposite way, but the length is the same. Okay, in other words, that b has the same length as minus b but points in the opposite direction. That's what I told you. We just flip the factor. Okay, that is the short way to tell. So the subtraction of factor b from factor a is just simply the addition of minus b to a. Okay, so a minus b factor, okay, can be written as a factor plus minus b factor. So this is very simple. So let's take an example for you to understand this more clearly. So say that you have in this case a woman sailing a boat at night in following direction. Okay, so first sail 27.5 meters in the direction of 66 north of east, then travel 30 meters in the direction of 112 degrees north of east or 32 west of north. And then if the woman makes a mistake and travels in the opposite direction for the second leg of the trip, then where will she end up? And compare this location to the location of the duck. Okay, so here's how we solve this problem. So we can represent the first leg of the trip with the factor a and the second leg of trip with factor b. You can take any other letters I don't mind. Okay, this is just for our convenience in this discussion. So the duck is located at say point a plus b. Okay, because this is just the result. The result is the addition or the summation of these both factors. Okay, so if the woman mistakenly travels in the opposite direction for the second leg of the journey, then it must be a minus b, right? And it means that b, which is the same magnitude, but the direction is the opposite, which is 180 minus 112, which is 68 degrees south of east. Okay, so let's see how we draw it. This is so we can solve it as usual. So first determine the location at which the woman arrives by accident. Draw the factors a and minus b. Then place the factor head or tail. Then draw the resultant factor r as shown in the slide. Okay, there is the factor r. It is figure b just on the right side of the point tree. Then we use a ruler because this is graphical way. You want to do analytical way later, this is also a result in the same thing. Okay, so in this case r is about 23 meters and theta is about 7.5 degrees south of east. Okay, and the fifth step is to determine the location of the duck that actually needed to be reached. So we repeat this method to add factor a and b without um, taking the opposite. Okay, so say that this is resultant factor R accent. So R accent is 52.9 meters and theta is 90 90.1 degrees north of east. Okay, it's about that value. The way of solving this graphically is shown in the right side of the slide. So you can see that the woman will end up a significant distance from the dog if she travels in the opposite direction from the second leg of the tree. So yeah, that's done for the example. Now let's learn how to do multiplication of factors and scalars. This is actually easy. If we decided to walk 3 times, for example, um, then actually we just walk 3 times 27.5 meters, which is actually just, yeah, straightforward, 82.5 meters in the direction of 66.0 degrees north of east. This is from a previous example. Okay, so yeah, by multiplying a factor to a scalar, we just multiply the value, and the direction keeps the same. If okay, so there's a condition if we multiply to a positive scalar, but if the scalar is not positive, it's negative, then the magnitude stay the same, but it will change the direction. It means that if it is yeah, I'll show you in for the example. Okay, so for example, if you multiply -2, this is a scalar to a factor, then the magnitude will doubles, but the direction will change. Okay, so here's the summary. When factor A is multiplied by a scalar of C, then the magnitude of the factor becomes the absolute value of CA. And if C is positive, then the direction of factor doesn't change. And C is negative, then the direction is reversed. How about if C is 0? Actually, you will rarely find this condition, but yeah, if C is 0, then actually it will result in the magnitude 0 and direction also 0. Okay, so in our case, that C3 and A 27.5 meters, the factors are multiplied by scalar in also many situations. Okay, not that division. Okay, so now we enter the realm of division. Division of factors actually the inverse of multiplication. For example, we divide by 2. It means the same as multiplying by a value of half. Okay, the rule of multiplication of factor by scalar and the division of scalar is actually the same. Simply treating the divisor as a scalar between 0 and 1. So in the examples above, we have been adding factors to determine the resultant factor. And in many cases, however, we'll need to do the opposite. Okay? We'll need to take a single factor and find what are factors added together and produce it. So we need to find the component of a single factor in the x and y components. This is what we'll discuss now. So for example, we want to know the we may know that the total displacement of a person is 10.3 blocks in a direction 29.0 degrees of northeast, and we are about to find how many blocks actually going east and north when she walk. So actually this method is called finding the components or parts of the displacement, and this is just the inverse process of what we have done before. So most of the process here involves finding components along perpendicular axis, which is yeah, it can be north south, east west. Okay, so that right triangle techniques can be involved. Okay, so let's learn about it. Yeah, we do it by analytical methods. Okay, so analytical methods of vector addition and subtraction employs geometry and simple trigonometry rather than ruler and protector that we do when we are using graphical methods. Okay, so yeah, of course we need to sketch first to get a clear image of what we are going to solve. But yeah, that's just one step of many. Yeah. So, for example, given a factor like a in figure below, so we may wish to find which two perpendicular factors x and ay will add and produce this result. So ax and ay are defined to be the components of a along the x and y axis, and it is very clear that factor ax plus factor ai will result in a factor a. And please note that this relationship between the factor components and the resultant factor holds only for factor quantities, okay, which include both magnitude and direction. Okay, so if we only consider the magnitude and not considering the direction, it will result in wrong. So the magnitude of ax plus the magnitude of ay will not be the same of the magnitude of a. Okay. So if the factor is known, then its magnitude a and its angle theta are known. Then to find ax and ay, we just simply using this formula in a slide on a slide, which is ax is a cos theta and ay is a sin theta. So let's work for an example. So consider the picture below. That we can see clearly that a, the magnitude of a is 10.3 blocks and the theta is 29.1 degree. So that ax is just 10.3 cos 29.1 degree, which is 9 blocks, and ay is a sin theta, which is 10.3 times sin 2.1 degree. 29.1 degree actually, I mistyped it, which result in 5 blocks, about 5 blocks. Okay, this is rounding up result. So if the perpendicular components ax and ay of a factor a are known, that then we can also find it analytically. So to find magnitude of a and direction of theta of a factor for its perpendicular components, we need to use the following relationship. Okay, so the a is, yeah, we can do it by using the Pythagorean theorem, which is the square root of the square root of the sum of ax squared and ay squared, whereas the theta is just the arctangent of ay by ax. Okay, so you can see that the figure shows you that if it is known that ax is 9 and ay is 5, then a is the square of 9 squared plus 5 squared, which is 10.3 blocks. And also the direction is the arctangent of 5 by 9, which is 29.1 degree s. Okay, that's done for our lesson today. This is just a very short introduction for our new chapter on kinematics for two-dimensional motion. Okay, here's a little inspiration for you today that Serena Williams once said, "A champion is defined not by their wins, but by how they recover when they fall." So always remember this. Okay, you may not succeed every time, but you need to keep moving and keep standing up from your failure. Okay, so yeah, thanks for watching. Subscribe, give a like, comment, and share this to your friends. I'll be back on every Tuesday and Thursday. And don't forget to visit our website on https science with exposd.uneworks.com to access your free learning resources. Keep watching and be thoughtful. Goodbye and see you.